Law is perhaps one of the most important laws when it comes to circuits. It's the law that tells us about the relationships between voltage, current, and resistance. And Ohm's law is best expressed with an equation. The equation tells us that the voltage, or the potential difference, delta V, is equal to the current times the resistance of our object. Delta V, as I mentioned, is voltage, which is another term for potential difference. Voltage is the name that's commonly used when we're dealing with circuits. We know I is current, measured in amperes, and R is resistance, measured in ohms. Any object that follows Ohm's law, in other words, any object that has its resistance be equal to the ratio of the potential difference divided by the current, is said to be ohmic. Almost every object that we deal with in this class will be ohmic in nature. I mentioned Ohm's law is a very important law, and so let's look at an example using Ohm's law. In this example, it tells us that currents that exceed 100 milliamps can be lethal to humans. We know that dry skin has a resistance of approximately 100 kiloohms, and so we're going to find out what is the maximum safe potential difference between the fingers, between a thumb and pointer finger of someone who accidentally touches a live wire. As we're analyzing this problem, we're going to use Ohm's law. We can always assume that things are ohmic unless we are told otherwise. So I know that I can use Ohm's law to find this maximum potential difference by using the fact that that potential difference is equal to the current times the resistance. It says that currents exceeding 100 milliamps can be lethal. So I'm going to assume that 100 milliamps, or 0.1 amps, is the maximum safe potential current. And we know that our resistance is 100 kiloohms. I will, of course, have to convert that. So that would be 100 times 10 to the third ohms. My 0.1 amps times 100 times 10 to the third ohms. All I have to do is move the decimal points one to the left, or one to the left. And so I end up getting 100 times 10 to the second volts, which in proper scientific notation would be 1.00 times 10 to the fourth volts. In other words, the maximum safe potential difference is 10,000 volts. That's a pretty big potential difference. So luckily, with that current, you can deal with pretty large potential differences. However, Part B talks about what happens if his fingers were wet instead. The resistance of wet fingers drops quite a bit to 1 kiloohm rather than 100 kiloohms. So in Part B, we'd be replacing that resistance with, I'm going to write that as 1,000 ohms. And when we multiply 0.1 amps times 1,000 ohms, we end up with only 100 volts. That's a really important number when you realize it, because the voltage of the plugs in our outlets exceeds 100 volts. If you have wet fingers, you could potentially kill yourself by touching something that is plugged into the wall. This is why you always see those warnings on outlets to, for example, on a hairdryer, never use this while you're in a bathtub, because you could actually electrocute yourself with something like that. We'll have a lot of experience using Ohm's law as we analyze circuits in the next few days.